Today we're going to talk about a new theory of gravity. We're going to look at the maths behind that gravity, and we're going to use that maths to compare it to data for the galaxy rotation curve problem. And hopefully our new theory of gravity and the maths behind that will prove that we can solve the galaxy rotation curve problem. Let's get started. Gravity. So when we think about gravity, or we think about our knowledge of gravity, we can start with classical gravity, which is Newtonian physics. This is great for looking at gravity for anything on Earth, which is where we use most of our equations in the classroom. So anything from a grain of sand up into a solar system works well with Newtonian gravity. Then along came general relativity, and this was a better theory for gravity, which also includes relativistic effects. But it doesn't include quantum gravity, which is a major problem in today's physics. It also doesn't account for dark matter, which accounts for 85% of the gravity in our universe. So despite having an excellent theory for gravity, we still have some holes. All right. Here's our new theory for gravity. It can be summarized in a very simple equation, G equals Vxm over A. What does that mean? Well, this introduces some new hypothetical concepts. First of all is Vx. Vx stands for the amount of gravity per kilogram per second. And A stands for the distribution of gravity. Okay, so before we get started, let's first rearrange our thinking a little bit, so some abstract concepts. First of all, we need to imagine that gravity is a physical thing, that we can think of gravity as something that is physically present and takes up space, takes up volume, and that is produced by mass, and it is produced by mass at a constant rate. And therefore, if it is a physical thing, we can quantify it. Okay, so we can then create a theoretical term to quantify gravity, and this term is I've labeled Vx. Vx stands for the amount of gravity created by a kilogram of mass per second, and Vx is equal to 8.387 times 10 to the negative 10 meters cubed per kilogram per second. That means that 1 kilogram of mass produces 8.38 times 10 to the negative 10 meters cubed of gravity every second. The other term we need to talk about is the distribution of gravity. The distribution of gravity is a representation of how gravity is distributed around an object. So we classically imagine gravity as equally distributed around the center of a mass in all directions. In this case, we can calculate the distribution of gravity as a surface area of a sphere, where the radius of that sphere is the distance to the center of that mass. So if we take a distance from the center of a mass and we look at all points of equal distance, this will create a sphere. And we can say that the distribution of gravity is equal to the surface area of the sphere, which is 4 pi r squared. If we take a closer distance, then we have a smaller distribution of gravity. If we take a further distance, then we have a larger sphere and a larger distribution of gravity. So we can now take our formula for gravity, and for all classical gravitational problems, we can now use the distribution of gravity as equal to 4 pi r squared, which makes our formula gravity equals the volume of space consumed per kilogram per second times the mass in kilograms divided by 4 pi r squared. That's all very interesting, but how does it work in real life? Well, here are all the objects in our solar system. Here is the mass of these objects in kilograms, the radius of these objects in meters, the volume of space consumed per kilogram per second, and here is NASA's calculations for the gravitational acceleration on the surface of each of these objects. This is our formula for the gravitational acceleration, and as you can see, our calculated gravitational acceleration is extremely similar to NASA's calculation for gravitational acceleration. Effectively, we can say that our new formula gives us a mathematically identical result to Newtonian physics for all classical gravitational problems. What about rotating objects? Rotating objects are not spherical. As they rotate, they flatten out. They become oblate spheroids. According to classical physics, we would expect gravity to be different on the poles compared to the equator. That is because as the object flattens out, the distance from the center of the object to the poles is shorter, and so would have a greater gravitational acceleration. The distance to the equator is further, so it would have less gravitational acceleration. In addition to that, the equator also has a rotational speed and therefore has a centrifugal force acting on it. This would reduce the gravitational acceleration at the equator and therefore would increase the discrepancy between the gravitational acceleration at the poles and at the equator. But this is not correct. The gravitational acceleration is the same over the entire surface of the mass.
There's something I've been wrong about for decades. So I spent my whole life saying Santa on the North Pole would be the only person who would know his true weight.
Right.
Because on the equator, you're weighing less than your true weight.
Right.
True gravitational weight.
Okay.
There are two things messing with your weight at the equator. Because the Earth is bulged, you are farther away from the center of the Earth, and it's spinning. That's wrong.
Uh-oh.
Here's the deal. It turns out everywhere on the geode, you weigh exactly the same.
What?
If the Earth bulges from spinning, if you bulge at the equator, the poles come in a little bit.
Down, right?
Okay? So now it sounds like I'm closer to the center of the Earth, I should weigh more. However, not the entire Earth is pulling on you. It turns out that while you are closer to the center of the Earth, there's less mass pulling on you. You can do this, you can show this with calculus and Newton's laws of gravity, that if you are smaller from pole to pole, the only part of Earth attracting you is the sphere that is the cutaway between your feet and the center of the Earth. And that sphere does not include the bulging that comes outside of that sphere.
Okay.
Those factors combined exactly equal the factors that affect your weight here on the equator, because the entire mass of the Earth is pulling on
you because you're at the center.
Okay, because you're at the widest point.
Right.
Now, what is the sphere beneath your feet? It's got everything.
It's all of it.
All of it.
It's all of it. So these two things, these two, principles, if you want to call them, they cancel out.
Yes, they exactly cancel. The fact that you have the whole Earth pulling on you, yet we're spinning,
right?
Okay, so you have all the mass of the Earth, but the spinning, so that makes you weigh more, but then you're spinning, that makes you weigh a little less, plus the Earth is a little wider, so that makes you weigh a little less. Okay, all of that.
You put it together.
It comes out in the wash compared to your weight on the pole.
Wow. So Santa's fat behind can walk down to the equator
and weigh
exactly the same.
Exactly the same thing. Check this out. You ready? Okay. If Earth spins faster.
Right.
This is true. If the Earth spins faster, if it spins once in 90 minutes instead of once in
24 hours,
then the centrifugal forces will be so great that you weigh nothing on the equator. You'll just float.
You just float?
You just float.
Can we have that, Earth, please?
Okay, now watch. How do I know that's true? Because the space station, everything orbiting in low Earth takes 90 minutes to go around.
There you go.
So if Earth's equator takes 90 minutes, it'll be you're weightless like the space station. Okay?
So, right.
However, Earth won't keep its spherical shape.
It will become a pancake?
Yes! This is the fun part. Oh my gosh. Okay? So we think of Earth as solid, but it really isn't.
Right.
Okay? There's plasticity in the mantle. Right. There's rocks that'll just start floating. Okay? So the Earth will start flattening. As it flattens, the equator gets wider and wider and wider and you are weightless out there. Well, how about Santa? These guys. Well, if Earth becomes this huge disk, what happens to the North and South poles? How much mass is between them and the center of the Earth?
Nothing.
Nothing.
That's it.
So therefore, how much do you weigh?
You don't weigh anything.
And so everybody still weighs the same.
That's pretty wild.
It's wild.
Except you're floating out there.
You're floating out here, but no matter where you are on it,
you weigh the same.
You weigh the same, which is zero.
Right.
Because on the poles, there's no mass between you and the center of the Earth, because you are at the center of the Earth, because you flatten to a pancake. I was so surprised by the possibility of this that I had to calculate just to make sure. No, and then I got the results like, oh my gosh, this is a beautiful fact of physics.
The gravitational acceleration is the same over the entire surface of the mass.
Everywhere on the geode, you weigh exactly the same.
So how do we account for this? Well, the classical explanation for this is that we're only taking the mass inside the radius to the center, which accounts for the gravitational effect. So if we're standing on the poles, then we're only taking the radius underneath our feet as the mass, which is contributing to the gravitational effect. We're excluding all this additional mass, which is not inside our radius. As we move to the equator, our radius increases and incorporates more mass, and so therefore the gravitational acceleration increases with additional mass, therefore accounting for the discrepancy between the poles and the equator. Therefore, the gravitational force is equal to all points on the surface of the mass. The problem with the classical explanation for this is that it ignores all mass outside of the radius of the center. So if we were standing at the north pole of this mass, then all the mass within the radius would contribute to our gravitational acceleration, but none of the mass outside would contribute. This is a significant proportion of mass that has no gravitational effect. It's counterintuitive to imagine that the mass with close proximity to us has no gravitational effect, yet mass furthest distant from us still does have gravitational effects. Why would we include some mass and not others? Conceptually, it doesn't quite fit. So this is mathematically accurate. The gravitational acceleration is the same at all points on the surface. But conceptually, this does not make sense. Why include some mass and exclude other mass? This becomes more clear when we look at the gravitational effects around a galaxy, because a galaxy is 85% dark matter, and the dark matter is distributed everywhere. So if we look at a star on the outskirts of a galaxy, according to our current understanding of gravity, we would say that all the mass within the radius of that star would contribute to the gravitational acceleration of that star. But if we are looking at the mass around that star, then we would be saying that more than half the mass around the star has no gravitational effect on that star, and that the mass on the other side of the galaxy, much, much further away, has more gravitational effect than the mass directly next to the star on the opposite side. We can better account for this discrepancy using our new formula by saying that the shape of the mass represents the distribution of gravity.
Everywhere on the geode, you weigh exactly the same.
If the mass is in the shape of an oblate spheroid, and the distribution of gravity is in the shape of an oblate spheroid, then it is easier both mathematically and conceptually to calculate gravity using the distribution of gravity as an oblate spheroid. So this gives us our new mathematical equation where G equals Vxm over A, where A is the surface area of a spheroid or the surface area of our mass. We know that gravity is equal at all points on the surface of this mass, so we can use one equation with one mass to calculate all points on the surface of that mass. If the shape of the object represents the distribution of gravity, then the surface area of an object will equal the distribution of gravity. In the case of the Earth, the surface area of the Earth can be calculated using the surface area of an oblate spheroid.
Now, Earth bulges. We are about 5 miles wider across the equator than we are pole to pole.
Okay.
So since we're squashed pole to pole, that makes us oblate.
Okay.
And we're not a perfect sphere. It's a spheroid. It's an oblate spheroid.
Okay.
And
there are two formulas we need to know to calculate a surface area of an oblate spheroid. We need to know the eccentricity, which in the case of the Earth is 0.0812. The eccentricity is a measure of the flatness of the sphere. Once we have the eccentricity, then we can calculate the surface area of a spheroid using this formula. And that tells us that the surface area of the Earth is approximately 5.1 times 10 to the 14 meters squared. We can now take the surface area of the Earth and include it into our equation. So our equation says that the gravitational acceleration on the surface of the Earth will be equal to the Vx times the mass of the Earth divided by the surface area of the Earth. And this comes out as a gravitational acceleration of 9.819. This gives us a universal gravitational acceleration for the surface of the Earth, as opposed to Newtonian or classical physics, where we calculate each individual point relative to the center of the Earth.
so in the universe, you have exceptions to this when you have rapidly rotating objects.
Okay.
Guess what happens to them?
They flatten out.
They flatten out. Saturn rotates once every something like 10 hours.
Wow.
Saturn is big and it rotates twice as fast as we do.
That's
My
serious.
boy's flattened.
Yes.
10% flattened. It's 10% shorter pole to pole than side to side.
Wow.
Next time you look at a photo, check that out. You can notice it easily
notice it, right.
with your eyes.
Okay.
Saturn is a great example of an oblate spheroid. It is a gas planet with a fast rotation, so it is 10% flatter from the poles as it is to the equator. It has an eccentricity of 0.43. We can work that out using this formula. And the surface area of 4.27 times 10 to the 16 meters squared using this formula. Therefore, using our new equation, we can calculate the gravity on the surface of Saturn as 11.2 meters per second squared. We are saying that the gravitational acceleration is equal at all points on the surface of Saturn.
Everywhere on the geode, you weigh exactly the same.
So, when we're talking about rotating objects, I would argue that our new formula, one, is mathematically simpler, taking one equation and doing one calculation for one object, as opposed to taking a spectrum of calculations depending on the location on the surface. It is conceptually more intuitive, as we're not excluding any mass from our calculations, and it better predicts gravitational acceleration around all rotating objects, anything from the Earth, Saturn and Jupiter, to other stars, neutron stars, pulsars, or rapidly rotating black holes. But what about the galaxy rotation curve problem? If you don't already know, the galaxy rotation curve problem is one of the sources of evidence for dark matter. When we look at the rotational speed of stars and galaxies, we see that the rotational curve remains flattened as we move further from the center of the galaxy. However, classical physics and our understanding of gravity, we would expect that as we are further away from the center of the galaxy, for that velocity to decrease. When we're looking at the distribution of gravity, if the shape of an object represents the distribution of gravity around that object, then we can calculate the distribution of gravity using the shape of that object. In a non-rotating mass, we can use classical Newtonian physics, or we can use the distribution of gravity as the surface area of a sphere. As an object rotates, it becomes an oblate spheroid, and so the distribution of gravity can also be mimicked by the shape of that object, and we can use the shape of an oblate spheroid to calculate the distribution of gravity. When we look at a galaxy, most galaxies are, or many galaxies, are in the shape of a flat circular disk. So, galaxies come in all shapes and sizes. For simplicity, let's just use the surface area of a circular disk to calculate the distribution of gravity for galaxies. So, surface area of a circular disk is equal to 2 pi r h, and we are calculating h as the square root of 2 times the mass. So here is our new formula. Gravity equals Vxm divided by this distribution of gravity. And in this case, we're using a disk, which is 2 pi r h. And so we can say that gravity equals Vxm divided by 2 pi r square root of 2 times the mass. All right. This is galaxy M33. And this is a graph of gravity over radius. The gravity is in meters per second squared. The radius is in meters. The blue line is the predicted gravitational acceleration of a galaxy calculated from the orbital velocity of that galaxy. The orange line is the expected gravitational acceleration of that galaxy calculated from the visible mass of that galaxy. You can see there is a significant difference between the blue line and the orange line. This is currently accounted for by the addition of extra mass in the form of dark matter. Our new equation takes the visible mass of that galaxy and calculates a new gravitational acceleration. And as you can see here, using the visible mass of that galaxy alone, our calculation more closely resembles the observed gravitational acceleration in that galaxy. We can also calculate the orbital velocity using the same equation. We can derive the orbital velocity at the point where the centripetal acceleration equals gravitational acceleration. So centripetal acceleration equals gravitational acceleration. We know the formula for both, and we end up with this new formula. Here is our galaxy again, galaxy M33. This graph is orbital velocity over radius. Again, the blue line represents the observed orbital velocity of that galaxy over the radius. The orange line represents the expected or predicted orbital velocity given the visible mass alone. And the discrepancy between the blue line and the orange line is accounted for by additional mass in the form of dark matter, which is yet to be discovered. However, our new equation, the grey line, can now predict the orbital velocity of this galaxy better using only the observed mass of that galaxy. We can also rearrange our equation to give mass of the galaxy from its observed orbital velocity. So we have our orbital velocity formula, and if we rearrange that, we can get it to show us the mass from the observed orbital velocity. And again, this is our galaxy M33. The blue line is the observed mass, the visible observed mass of that galaxy. The orange line is the expected mass of that galaxy given its orbital velocity. And again, you can see a large discrepancy between the visible and expected or predicted mass. And that predicted mass is accounted for by dark matter. However, our new equation takes the observed orbital velocity and calculates very accurately the visible or observable mass in that galaxy, therefore eliminating the need for dark matter. Okay, so in conclusion, we now have an equation for gravity, G equals Vxm over A. This equation can calculate classical gravitational problems as accurately as Newton's formula for gravity by using the distribution of gravity as a sphere. It can calculate gravity for rotating bodies using the distribution of gravity as a surface area of a spheroid. And it can now calculate the orbital velocity or the gravitational acceleration of galaxies using the distribution of gravity as the surface area of a disk. And the most important point here is that this equation can calculate the predicted gravitational acceleration of galaxies without the need for dark matter. It can be adapted to predict the orbital velocities of galaxies from visible matter alone without the need for dark matter. Or it can calculate the visible matter from the orbital velocity of that galaxy, again excluding the need for dark matter. There's also a lot more that this theory can contribute to that we have not discussed today. Some examples of this include other phenomena associated with dark matter, such as gravitational lensing, galaxy clusters and collisions, cosmic microwave background radiation, and the cosmic web. It can also be incorporated into quantum gravity because it works with a finite total gravity, eliminating infinities. Therefore, we can now calculate that the smallest non-rotating black hole needs at least the mass of 3 suns in order to form a black hole, even if it had 0 volume. And now we eliminate infinities from small objects like particles because each particle has a finite amount of gravity. It is also not based on relativistic maths or relativistic time or fields, and so therefore is easier to incorporate this into quantum gravity. It can also predict relativistic effects such as the speed of light and why the speed of light is constant, why light bends due to mass and gravity and gravitational lensing. It can help predict the curvature of space-time, the constant speed of light, as I've mentioned, and it also helps explain other things like dark energy, quantum mechanics, electromagnetic waves, time, and the structure and movement of the universe. But unfortunately, these are all topics for other presentations. We do not have the time to go into this in this presentation. So I'm going to end it there. Thank you very much for your time. If you like this video, check out some of the others.